Hello and welcome to tutorial 3 from MH1801. This is about using integrating factors to solve differential equations. The kind of differential equations that we are interested in today are those of this particular form, which we shall call star. We have a function f of x times dy dx plus its derivative f prime of x times y, and it equals to some function in terms of x, h of x. Two very important concepts are being used in trying to solve such a differential equation. The first one is implicit differentiation, and the next is the product rule for differentiation. If we have a function in terms of y, let's call it f1, then we can compute the derivative of f1 of y with respect to x using the chain rule. So what we do is that we differentiate f1 of y with respect to y and then multiply by dy dx. So what this gives us is f prime of f1 of y times dy dx. Now for the product rule, if you have two functions, u times v, let us suppose you want to compute the derivative of the product. Then this thing is given by u prime times v plus u times v prime. Okay, and using these pieces of information, you see that the left-hand side in our differential equation is precisely something for which we can apply the product rule. F and its derivative f prime appear, and y and its derivative dy dx also appear on the left hand side. So indeed, we can apply the product rule for differentiation. In other words, we can convert the left hand side into a single derivative, d of dx times f of x times y. We are taking the derivative of f of x times y. The right hand side is unaffected. How do we extract y from this expression? To do that, we make use of integration. We will simply integrate both sides of our differential equation. Using the fundamental theorem of calculus, differentiation and integration are sort of inverse to each other. They're inverses of each other. So in a sense, they will cancel and give us fx times y. On the right hand side, we will have an integral to deal with. So what we get when we do integration should be fx times y on the left, and on the right, the integration of h of x. Let us suppose that we can integrate h of x, and we produce it as a function g of x plus our arbitrary constant c. So to get to y, we make the assumption that f of x is not equals to 0. Let us suppose it is true. If it is, then you can divide throughout the expression by f of x, and so we can produce y in this form: g of x plus c divided by f of x is equal to y, and that is the solution to our differential equation. Of course, we need to note that we should check this condition: fx is not equals to 0. We should check that this condition holds true before we can obtain the solution in this form. More generally, we may not have a differential equation of the form star. What we may have is a differential equation of this form. We may have two functions in terms of x, f1 and f2. How are we going to deal with this situation? What we will try to do is to re-express this differential equation into the form star that the first thing that we should check for is whether f2 equals to the derivative of f1. Whether this f2 is f1 prime of x. If it is, then already we don't need to worry because this equation is already in the form that we want, in this form star. Here we have f1 and here we will have f2, which is equal to f1 prime. So that is okay. If it is not in this form, so if not, then we shall try the integrating factor approach. We will make a special condition, or we will have to use a special condition. f1 of x is not equals to 0. If this holds, then we can divide throughout our differential equation by f1 of x. So we will get this expression. This is of the form dy dx plus a function in terms of x, f3, this function, and h of x, yet another function in terms of x, this function. So this is what we have. The next step is to introduce our integrating factor. We check if we can compute the integral of f3 of x. At this stage, we will integrate it, but we don't need to introduce the arbitrary constant c. We will do it right at the very end. We don't do it at this stage. If we can compute this integral, then the integrating factor that we use to multiply throughout our differential equation is e to the integral of f3. So that is what we do next. We multiply our integrating factor e to the integral of f3 to every term in our differential equation. What is the key thing to note here? The key thing to note is that when you differentiate e to the integral of f3, you are able to write it in a very nice form. We will first integrate the exponential, so it reappears here on the right hand side. We didn't need to do anything about it, but then we must multiply by the derivative of whatever is in the power, so the integral of f3 of x. Using the fundamental theorem of calculus, because differentiation and integration are sort of inverses to each other, this term is simply f3 of x. And you see that it is right down here. Therefore, we have converted this version of the differential equation, double star, into the form star. F of x in our story is precisely our integrating factor e to the integral of f3. And we have gotten our differential equation into the form that we want, so that we can apply the procedure from above to solve the differential equation. We can get to this stage, integrate, and solve for y as we did before. This is the method of using an integrating factor to solve our differential equation. Of course, if we have any initial value, we can use it to solve for the constant c, and that will give us the solution to the corresponding initial value problem. So this is the method that we will use to solve the questions in our tutorial.